Welcome to my channel. Today I'm going to discuss how to calculate the diameter of Earth's umbra at any given distance from Earth. In an earlier video I discussed how to calculate the length of Earth's umbra. You will recall that in astronomy the word umbra refers to the conical solid shadow that extends out behind any solid body, like the Earth, and where, in this case, the sun's light is fully blocked by our planet. Of course, every night we rotate into Earth's umbra. We tend to view it as if only the surface of the Earth gets dark. But the Earth's shadow that brings us night extends out into space. As we discussed in the Earth's umbra length video, the full shadow reaches out into space 858,317.7 miles. Here on the surface of the Earth, we are at the widest point of the cone. The base of the cone is a circle that passes through the center of the Earth, and it is oriented perpendicular to the line running through the center of the Sun and the center of the Earth. As the shadow moves away from Earth into space, it grows narrower, following the typical shape of a cone. In this video, we will see how to calculate how wide that shadow will be at any distance we choose. To set the limits, naturally, if you are on the side of the Earth facing the Sun, there is no visible umbra at all. If you move away from the Sun behind the Earth, past the point of the apex of the cone, you will be out of the shadow again, and will be able to see the Sun. So, our calculations will only be concerned with the range of 0 miles from the center of the Earth out to a point 858,317.7 miles from the center of the Earth. The Moon is one object that passes through the Earth's umbra, and we will talk about that at the end of the lecture. As we move away from Earth's center, the diameter of the cone will narrow. But by how much? We begin by choosing a distance, either because we know an object that will be located there, or because we just want to know how wide the shadow is at that point. We will label that distance L sub O, and it will represent some given number of miles from the Earth's center. In this image, we have all the elements labeled that we will need to do our calculation. The large triangle represents half of the entire umbra vertical cross-section. Its vertical side is labeled R sub E, and its length is the radius of the Earth. Its horizontal side is labeled L sub U, and it represents the length of the Earth's umbra. Here are the values we established in my Calculating Earth's Umbra Length video for L sub U and R sub E, and it is an easy calculation to also establish D sub E by multiplying R sub E by 2, and that gives us the diameter of the Earth, which is 7,917.6 miles. Having these two sides of our right triangle is all we need to calculate angle theta. Once we have R sub E and L sub U, we are all set. And angle theta is the angle of the triangle sitting at the apex, which will be used for working with the smaller triangle as well. It is therefore critical to our project. By dividing R sub E, which is the opposite side of the triangle, by L sub U, the adjacent side of the triangle, we can find the tangent of angle theta. Here we insert the values and end up with 3,958.8 divided by 858,317.7. And that gives us the tangent value for the angle theta, which is 0.004612. And by using the inverse function on our calculator, we arrive at the value for theta of 0.26425 degrees, just over a quarter of a degree. We are attempting to calculate the value of the diameter of the umbra at a given distance L sub O from Earth, labeled D sub U. Half of that value is the radius of the umbra at that point, labeled R sub U. R sub U forms the opposite side of the smaller triangle. The adjacent side of the triangle is labeled L sub OU, and the angle theta is part of this triangle as it was with the larger triangle we were working with before. We don't know the value of R sub U yet, but we can get the value of L sub OU by subtracting the given value L sub O from the known value of L sub U. If you take away the value of the distance you move away from the center of the Earth from the entire length of the umbra, what is left is the distance from the point labeled D on this diagram out to the point labeled A, sitting at the apex of the cone. We now have the length of one side of the triangle, L sub OU, and we have the value for the angle theta. Now, what can we do with these values? Moving back to our tangent equation, we can algebraically manipulate the equation by multiplying both sides by the length of the adjacent side. That leaves the length of the opposite side isolated by itself. And we then swap both sides so that it is now on the left side of the equation. R sub u is our unknown, and it equals the tangent of theta, which we do know, times the length of the adjacent side, which we can calculate with the information we have in hand, by subtracting L sub u by L sub o. Since we know the diameter of a circle is always equal to twice the radius, we end up with our equation at the bottom. We can now punch in some values that we have available to get a formula we can use for any point along the length of the umbra to calculate its diameter at that point. Twice the tangent of theta is 0.009224, and that is multiplied by the difference of 858,317.7 and L sub o, the distance from the Earth's center of the object in question. You can get a quick estimate of the value by subtracting the distance to the object from 860,000 and then dividing the result by 100. It will give you a ballpark value for the diameter of the umbra at that point. Let's do an example to show this formula at work. Let's use the moon as our object, and we'll see how wide the umbra is when the moon passes directly through it. Putting up our formula again, we now can fill in the value for L sub o with that for the distance of the moon, and that value is 238,900 miles. Remember that the moon's orbit is not a circle, but an ellipse, so its distance from the Earth will vary between 225,623 miles and 252,088 miles. We are using an in-between distance value for our calculation. Remember our down and dirty estimate rule? If you round that off to 240,000 miles and subtract that from 860,000 miles, you end up with 620,000 miles. Now divide that by 100 and you get 6,200 miles. We can check how close our estimate came after we do the rest of the calculation. Here we have the values inserted in the top equation, and once we do the subtraction, we are left with 619,417.7. We now multiply that by 0.009224, and it gives us the value of the width of the umbra at this point, 5,713.5 miles. Our estimate of 6,200 miles is within 10% of the real value, which isn't bad for a ballpark estimate. When we convert our value for d sub u to kilometers, we end up with 9,195 kilometers. If you do a Google search with "What is the diameter of Earth's umbra at the moon?" you will get 9,000 kilometers. Clearly, that is an approximate value, but it is very close to our value, which makes for a good double check on our work. If you enjoyed the video, please click like. And if you haven't subscribed yet, please do. Thank you for watching, and I'll see you next time.